Hello friends, welcome to Dr. Ossai Physiology Academy, DOPA for short. This is the place where we make the learning of physiology easy, exciting, and effective. Thank you for joining me. So today we're going to be starting a new topic, renal circulation and clearance. You can also call it renal blood flow. Okay, so we've talked about the structure of the kidney and how it relates to the general functions of the kidney. Now, I want to narrow down to the process of urine formation, okay? And you know that urine is a direct extract from the blood. Without blood, you cannot have urine. So the process by which urine is formed is related to the blood that flows into the kidneys. And it is now filtered, transformed through those three basic renal processes we mentioned before. If you can remember, filtration, reabsorption, and secretion. And then it is transformed into urine that is used to flush out wastes in the body, all right, through water. So let's get started. But always remember that learning about how the body functions, the mechanisms, which is what physiology is all about, can teach you vital health lessons, life lessons, and even management lessons. All right, so let's get started. So, renal blood flow is the first step. You need to understand it because anything that affects the renal blood flow, the blood that flows into the kidney, will affect urine formation. Let that sink into your mind. Anything that affects renal blood flow will affect urine formation. So now when urine is excreted, it's a product of this. Now excretion is equal to filtration minus reabsorption plus secretion. Okay? So it's just talking about the fact that in the glomerulus, there's filtration. It adds substances into the tubule. Remember that diagram of the nephron. Okay? Then reabsorption takes back stuff into the bloodstream, all right? Then secretion adds from the bloodstream into the tubule. So you need to understand this. Excretion is this, all right? So now we are talking about renal blood flow as it relates to urine formation. That's where we start from. So there's a basic understanding formula that you need to always remember. That whenever you're talking about flow, that means there are two basic things that are involved. Now, you talk about the pressure gradient. That's the difference between the pressure at 2 points, the beginning and the end, okay? And resistance. This is very basic. Flow is directly proportional to the pressure gradient. It means that if the pressure at the beginning is so great, is far greater than the pressure at the end point, it means that there will be a faster flow. Okay? So if you have, let's say, the pressure at the beginning point, which is the artery, the end point is the vein. Okay? Let's say it's 80 millimeters of mercury. And that in the venous side, the end point is just 40 millimeters of mercury. What's the difference? You have 40 millimeters of mercury as the gradient. But if you have something like this, 100 here, and you have 20, what's the difference? 80. So there's going to be faster flow Right? So you understand that. Now, resistance has to do with the diameter of the vessel. So many things influence resistance, but in this case, we're talking about the vessels, the blood vessels, things that can resist it from flowing. So it depends on how wide. A vessel that is this wide, stuff will flow faster than a vessel that is thin like this, okay? So, and we know that arterioles, the different generations, branches of the arterial system, from arteries, smaller arteries, down to arterioles before capillaries. So arterioles are the major blood vessels that control the diameter of the blood vessels because it has a lot of smooth muscles, okay, that can easily contract and then constrict the vessel. It becomes smaller, or it relaxes and it dilates the vessel, okay? So this is the main thing that controls the flow of blood. But now, let's now look at how this affects renal blood flow from this understanding. Now, the functional unit is the nephron, okay? The nephron is like this. This is the Bowman's capsule, okay? And this is the tubule. Now, the glomerular capillaries are here like this. Then you have the afferent. Remember, we have the afferent that supplies this. And we have the efferent, okay? The efferent goes like this and becomes the peritubular capillaries. All right? So, this is an arterial, afferent. So, the renal blood flow that enters into this unit, this system, is determined by the diameter of this afferent arteriole and this efferent arteriole. Okay? So, renal blood flow is dependent a lot on these two. So how, before you get to this arteriole, what are the other blood vessels? It's just good we know. It's not something you need to stress yourself about. It is good that you know. That's why we put up this diagram here. Now, first of all, you have the renal artery, which is a direct branch of the abdominal aorta. That means there's high pressure there, which we said before that it favors filtration, okay, because to lead to a high hydrostatic pressure. So this renal artery now branches. This branch here is called the segmental artery, okay? So when it branches, this is also a segmental artery, this is a segmental. Then when it curves and branches and enters by the side of this renal pyramid, remember this is renal pyramid, this here is referred to as the interlobar artery, okay? Then when it curves up to this point, from this point, it becomes the arcuate artery. So you see that from this arcuate artery, there are other branches. So this branch here becomes interlobular. Then from the interlobular, you now have the arteriole. That's this one now. The afferent arteriole. Okay, so from the high pressure, it goes, as it branches, it reduces. At this level of the arteriole, it has become about 60 millimeters of mercury, the pressure there. All right, so let's go back to this, the resistance. So what are those factors that determine the blood flow? In other words, we're talking about the factors that affect both the dilation and the constriction of these renal vessels. These are the two main things that control the blood that flows into this functional unit, which is the nephron. All right? So they are divided into two broad categories: extrinsic factors, or extrinsic regulation or control. You know, when you talk about regulation, it means control. Then you have intrinsic factors or control of renal blood flow. When you talk about extrinsic, what are you talking about? It means those factors, those control mechanisms that are external to the kidney, are outside the kidney, but they influence the renal blood flow. Then intrinsic factors are factors that are within the kidney itself that regulates its own flow. In other words, the kidney itself can regulate how much blood flows through these vessels. You call it autoregulation. Autoregulation. Whenever we talk about auto means self-regulation. Automatic means controlling itself. All right? So let's start with the extrinsic factors that regulate and control renal blood flow. One of them is sympathetic control. Extrinsic. One of them is what? Sympathetic control. So, what do we mean by sympathetic control? Remember that you have the autonomic nervous system, which is part of the peripheral nervous system. Just a quick recap. Nervous system, central nervous system, peripheral nervous system. Peripheral nervous system divided into autonomic nervous system and somatic nervous system. So under the autonomic nervous system, I mean system that is involuntary. Under involuntary, you can't control it yourself. You now have the parasympathetic and the sympathetic. Okay? So the sympathetic nerves, they are nerves. They do what? They innervate all these blood vessels, or blood vessels in the body. They are innervated nerves. All right? So these sympathetic nerves, when stimulated, they release norepinephrine or epinephrine, also known as noradrenaline or adrenaline. Okay? So that adrenaline or epinephrine, it has the function of helping to constrict these vessels. So what does it do? That means it reduces renal blood flow, because constricting it increases resistance. Once resistance increases, the flow reduces. Okay? So there's an inverse relationship. So sympathetic stimulation. But the thing is that because you have a very powerful intrinsic autoregulation, it usually overrides the sympathetic control. So sympathetic control under normal circumstances is negligible. Okay? Except in extreme circumstances, you lose a lot of blood. The sympathetic nervous system is stimulated powerfully. It will lead to a lot of constriction of these blood vessels, afferent and efferent, which will greatly reduce renal blood flow and may even stop you from urinating. Because once blood does not flow well into this place, urine cannot be formed. You lead to acute renal failure. Right? So another extrinsic, this is from outside the kidneys, angiotensin, number 2. Angiotensin 2. I'm sure this substance is we're familiar with it already by now. Angiotensin, angio, blood vessel, tensin, tenses it, constricts it. So we know what that does to this. It constricts, but there is something interesting. Angiotensin has more affinity. That's this efferent arterioles, they are more sensitive to angiotensin than the afferent. It has some important functional significance when we are talking of glomerular filtration now, especially glomerular filtration rates. We'll talk about this more. But for now, just know that it constricts, but more of this. So generally, it reduces renal blood flow because it increases the resistance. Another extrinsic thing there is AMP. AMP stands for atrial natriuretic peptide. Okay? This atrial natriuretic peptide, it does what? It dilates. So it's in favor of renal blood flow. But it does not dilate both of them. It dilates this afferent and constricts the efferent. Okay? But the dilatory effect on the afferent is more than the constrictor effect on this efferent. So what does it do overall? Because this one is more than this, so the overall effect is that it dilates and increases renal blood flow. So we have another one, the fourth one, prostaglandins. Have you heard of prostaglandins before? They are substances produced from arachidonic acids. You'll learn that more in biochemistry, this physiology. Okay, so prostate gland. So they were first discovered from the prostate. That's what gave them that name, prostate gland, prostaglandins. Okay, so prostaglandins, they are released during such extreme periods, just like we said, extreme periods where you lose a lot of blood, hemorrhage, they are released. And what do? They help to dilate. So you tell yourself, it's opposing the effect of sympathetic, instead of them to work together because they are released under the same circumstance of severe hemorrhage. No, they're not opposing them. It's a protective mechanism. Okay? So that this one does not lead to acute, because we said that it can lead to acute renal failure. So this one helps to manage it so that it doesn't go extreme. You will not get acute renal failure so quickly when you have severe hemorrhage. Okay, so prostaglandins, they dilate and they improve renal blood flow. So another one is proteins. Right? So proteins, the fifth extrinsic factor, they are more related to, you understand it from this intrinsic mechanism. So let's not talk too much about it now. So just keep that at the back of your mind. So let's go over now to intrinsic factors. All right, let's wipe here off. Intrinsic factors, that's factors that are within the kidneys that help to regulate it. Now, quickly, there are two. One is called myogenic control. Myogenic control mechanism. Then two is called tubuloglomerular feedback control. What do we mean by this? Myogenic control, tubuloglomerular feedback. These two are together known as autoregulation, like I've said before. Okay, so the myogenic control mechanism is related to the muscle, the smooth muscle in the walls of these arterioles. is just talking about the fact that when blood pressure increases, when blood pressure increases, blood flow increases. But you don't want to have too much blood flow in the renal. Why? If there's too much renal blood flow, it will increase urine production so very fast. Filtration is fast, everything is fast. So there's no enough time for both reabsorption and secretion. So you're not going to have enough waste that will be washed away. Okay? So if the renal blood flow also is too slow, there will be also accumulation of wastes in the system because it's not moving well. So you need a balance. And this myogenic control, generally both the myogenic and the tubuloglomerular feedback, they are effective in the range of 80 millimeters of mercury of blood pressure down to 180. That means even if your blood pressure varies this wide, if you see the difference, 100 millimeters of mercury difference, there will be little change in renal blood flow. That's exciting, that's powerful. See the difference in pressure, but renal blood flow does not change much because of these two powerful mechanisms. So when there is so much blood pressure, an increase in renal blood flow, the pressure expands these vessels. So the expansion of the vessels causes a stretching of the muscle. That stretching of the muscles causes action potential that activates, it opens certain calcium channels that now leads to contraction of the muscles. Okay? So the contraction of the muscle now constricts it. So instead of more blood flow, it reduces it to the extent to which it stretches it, the same proportion. So that helps to manage and balance the flow. Big blood pressure, high blood pressure, more flow, more stretching. That stretching causes constriction because the muscles are activated, because calcium enters due to that stretch. That's myogenic. Then tubuloglomerular feedback. What is it talking about? Tubules, glomerulus. You have the glomerulus first, tubules. So tubuloglomerular feedback is simply telling us what is happening at the tubules as the urine, the filtrate, goes along the tubules. It feeds back. It helps to control what is happening at this glomerulus, this filtration part. Okay? Because everything that happens, the flow here, everything starts from here. So what do we mean by that? Now, when there is, first of all, reduced flow, that means filtration will be slow and everything will be slow. It leads to there is more time for reabsorption of substances, especially of sodium and chloride. So reduced flow causes more time for this to react. So when you have more reabsorption of sodium and chloride into the bloodstream, what happens? The filtrate becomes more dilute. And do you know what happens? At that macula densa, you know that this tubule, from the thick ascending side, it touches this glomerulus, from which it now continues at the distal tubule. So that macula densa, at that point, they have cells that are sensitive to the concentration of the filtrate. They are osmoreceptors or chemoreceptors. So they sense the diluteness and then they release substances that dilate these afferent arterioles. So when the afferent arterioles are dilated, it increases renal blood flow, which increases filtration and increases the general flow of fluid. Remember that what initiated it was slowness of the flow. So it helps to correct it. So the same way when the flow is very fast, the fluid will not be too dilute, so it doesn't dilate it. So this is how it helps to control. But this mechanism is more powerful than this myogenic control, this tubuloglomerular feedback. So we've talked about the extrinsic, we've talked about the intrinsic, and now the next thing we need to talk about is how do you measure this renal blood flow? We know all the things that affect it, that control it. Now, how do you measure renal blood flow? That's what we're going to be discussing after this break. All right, welcome back. So we want to go into the next major thing that we need to talk about under this topic, and that is clearance. Because the concept of clearance will help us to measure blood flow. You know, discovery of some of these very intelligent, clever methods help us to do the impossible. Because ordinarily, if you say you want to measure renal blood flow, how do you want to do? That means you have to open the person up and put instruments there to measure practically, real life, the renal blood flow. Okay? But you can't do that in a human being. You can do that in animals. But in a human being, you can't use a direct means. So scientists, they always discover another way, an indirect way to achieve these amazing results that will give us something similar to the real value we are looking for. So let's see how renal blood flow can be measured. Okay? So now, remember that there is what enters into the kidney is equal to what comes out from the kidney through the veins minus what is excreted. Did you get that? The amount of substances that flow into the kidney through the arteries, they will equal the amount of substances that will flow out of the kidney minus the one that is excreted through this one. This is the ureter. Okay? That principle, what I just mentioned, it's called the Fick's principle. So it applies provided that that substance you are introducing that enters into is not changed, it's not transformed. That means it's not metabolized. Okay? So I've mentioned something, the amount of a substance. And guess what? Remember that in previous lecture, we gave a formula that concentration is equal to amount over volume. Okay? Concentration is equal to amount over volume. But now we're interested in amount. So amount is equal to concentration times volume. We want to get an important formula. All right? So we will need to introduce a substance into the blood that will enter into the kidney. And then what do? We'll measure that substance that flows out from the ureter to the urethra out. So we'll measure the concentration of that substance. All right? So we've understood this, that the amount is equal to concentration times the volume. Okay? So now, this substance, amount of substance that we'll need to introduce into the body, into the bloodstream, the plasma, it has to fulfill certain criteria. Remember that there are always criteria that they need to fulfill in order to give us the result that we need. And what are those criteria? We'll mention them. Okay, so the criteria number one is that this substance has to be freely filtered. Okay? The substance we are going to be introducing has to be freely filtered. Freely filtered. Number 2 is that this substance that we need to measure the renal blood flow, it should not be reabsorbed. It should not be reabsorbed. And number 3, it should be secreted. Okay? It should be secreted. I'll tell you the reason for all of this. All right? So, when this substance is filtered, because the renal blood flows into this afferent arteriole. It enters there, it's filtered. Not all of them is filtered, just a fraction, which is 20%. And then the remaining 80% flows there. This blood that is flowing carries substances. So, but we want to measure renal blood flow, including everything that flows. If we measure only what is filtered, it's 20% we are getting. That is why we said that it has to be secreted. So all that substance, almost all of it, have to be secreted back into the tubules. Okay? So it will give us, then number 1, that substance should not be lost. No, reabsorption takes it back. And we don't want that. We want all of the substance to enter into the tubules. So that's why it should not be reabsorbed, so I don't lose it. Then the ones that were not filtered, that pass through, they should be secreted. So which substance fulfills this criteria? It is called para-aminohippuric acid or para-aminohippurate. All right, this is how it's spelled: para-aminohippuric acid, known as PAH for short. PAH. Okay? It's an organic acid. It fulfills this criteria. Freely filtered, not reabsorbed, and it is basically secreted. Almost all of it is secreted back into the tubule and excreted. So another thing you can still add, it should not be metabolized. Of course, that's basic. Metabolized. Should not be metabolized, should not be toxic. Another one is that it should not alter renal plasma flow. So these are the things that this substance here fulfills. So that's what we use. So it's the ideal substance we need to measure renal plasma flow. So because we cannot do it directly, there are some assumptions we need to make. Because you know that when you are measuring the amount that is being excreted from the urine, you also need to measure at the same time the plasma concentration. The amount that is excreted has an inverse relationship with what remains. The more it's leaving the plasma, the more it's being excreted. So there are some assumptions that we make in order to use this method. Okay? So that assumption is that none of that substance is lost from the renal. The substance is introduced into the body, enters through this artery to the kidneys. Then because we assume that all of it is secreted into the tubules, so none of it comes here. So that means we don't need to measure anything here. That has solved that problem. Number 2 is that the substance that has been introduced into this, that enters the kidney, is the same concentration that can be gotten from any peripheral vein. The vascular system is a closed system. All right? So it means that we can just take from any peripheral vein, and whatever concentration we get is assumed to be equal to the concentration that enters here. So those are the two assumptions we make in using this method. So now we said that the amount is equal to the concentration. That's the urine concentration times volume. So we use this formula to get another formula. So this amount here is talking about the clearance, the amount of it that is removed. Clearance, first of all, is defined as the amount of a substance that is removed from a given volume of plasma per unit time. Okay, so that clearance now, C, the amount of a substance, okay, will be equal to the urine concentration. We refer to it as, use this symbol, urine concentration of PAH, okay, times the volume of urine that is formed. So we use this. It's known as urine flow rate. Urine flow rate. Okay? So this is the concentration. It's in milligram per milliliters, or can be gram per DL, but let's use milligram. Then the urine flow rate is in volume per time. That means milliliters per minute. Okay? So, and we said that the clearance, whatever is removed, is an inverse relationship with the plasma concentration. So that means that to be divided by plasma concentration, which is also in milligram per mil. So this one will cancel out this one. So clearance, the unit is in milliliters per minute. So this is the formula for clearance. So when we use this, we measure the urine concentration of PAH, para-aminohippuric acid. We measure the urine flow rate, how much urine is produced per minute. We keep it there. Then we go and measure the plasma from any peripheral vein. Then when we do that, we use this equation, and whatever we get, so we get the clearance of pH. So the clearance of PAH equals what? The renal plasma flow is in mils per minute. So when we do that, what do we get? We get 625 mils per minute. 625 mils per minute. That's the renal plasma flow. So you ask yourself, but we started with saying renal blood flow. But now we're talking about renal plasma flow because the cells are not filtered, okay? So, but we can still get the real renal blood flow. And we know that the difference between plasma and blood is cells, red blood cells. So how do we get that? Now, in the normal person, the hematocrit, or the red blood cells, the blood cells, okay, they form about 45% of the blood volume. Or we can say 45% is 0.5. Those are the cells, mainly red blood cells, okay? So 45%, that means there's remaining 55%. And that 55% is the plasma. So the plasma is 0.55. So if this 0.55 plasma, that means the whole blood is 1. Okay? Plasma is 0.55. Whole blood is 1. So what do we mean? We now said the plasma is 625. So if 0.55 is equal to 625, then 1, which stands for whole blood, will be equal to what? X. Okay? So you cross multiply. 0.55x is equal to 625. So the x now is equal to 625 divided by 0.55. So when you divide that, you get about 1,136 mils per minute. So that's the renal blood flow. Renal plasma flow is 625 mil per minute renal blood flow. You see how we derived it logically, easily. So that's how to get the renal blood flow. Okay? So you see that the renal blood flow is much for the size of the kidney, just this size, per minute. That's 1,000, talking about 1.1 liters flows through the kidney. So it gives you understanding how much this kidney needs blood flow for it to function. So these measurements, they enlighten us. So that's some of the lessons we can learn. You know, we talked about in some of the previous lectures that measurements, before anything that you cannot measure, you cannot control, you cannot manage, you cannot improve. So now that we have measured these things, what next? But first of all, what are the lessons that we can learn from all these things? Now remember, you ask yourself, PAH, para-aminohippuric acid, how did we discover that it's an ideal substance? These things are done through trial and error. Just keep trying different substances that you know, and then you hit the ideal one. Nobody was born with that knowledge. So for you to succeed in certain things in life, you need to do trial and error. And once you discover the ideal thing, it leads to a breakthrough and it leads to other discoveries. You know that before there used to be the computers that were made were very big because they were using what is known as vacuum tubes. But transistors were invented. And because silicon was first discovered, silicon is used in transistors. So that led to a breakthrough that made computers very small. So keep trying until you discover. It's like a revelation. You discover. So discoveries lead to breakthroughs. So that's one of the things you can. So another thing, we said that much earlier about the intrinsic regulation, extrinsic. That means for you to have consistency. Remember that this regulation is preventing instability from 80 to 180. It controls it at that level. So it means that for you to have stability in anything you're doing, consistency, stability, there needs to be self-regulation within you. Okay? Can apply to so many things. You are in a high office, and instead of stealing the money, you self-regulate. That self-regulation is something like, oh, if I take this money, God will not be happy. For those that are religious. So that's self-regulation. Then external regulation is like you put mechanisms in place that, oh, I cannot touch money. You put CCTV cameras and so on, or 3 people need to sign before money is withdrawn. Those are external mechanisms. The reason why Nigeria is not working is that we fail in putting mechanisms, especially external mechanisms. When it comes to public life, external mechanisms are more important that will help to regulate instability, corruption, and degradation in the system. All right? So that's something we need to learn. Self-regulation, external regulation are important. All right? So in all these things that we've learned, you can get more stuff. For further reading, I have written quite some books from renal physiology and other areas of physiology. Check the description box. You will see the links there that you can download it from Okada Books for a token. Okay? Just for further reading. See you in the next lecture.